Okay, so today we're working in chapter 6, which is about linear model selection and regularization. Okay, and so you know this is our linear model, right? The linear model looks like this. Okay, and then do they write the plus epsilon? Yeah. Okay. Okay, so this is our linear model, and a big part of this is, well, something happened. You know, part of it is trying to figure out which predictors do we use, right? Okay, that's a question that we might have, right? So we might have a bunch of predictors available. Maybe we don't want to use all of them, okay? Or maybe we do, right? Okay, and then how do we select the values of beta, right? Okay, so like when we fit the model to our data, okay, when we fit the model to our data, we're basically saying, well, here's my model. I got to figure out what values of beta to use, right? Do I say the intercept is this much and the slope is this much? How do I choose the best intercept and the best slope? Okay, and so for linear regression, for ordinary least squares, we use the least squares criterion. Okay, but you know, maybe we don't want to use least squares. Okay, so in OLS, okay, we select beta, okay, or we find the values of beta with the least squares criterion, right? Which basically says pick, you know, like for simple linear regression, it's basically pick your slope, beta 1, and intercept beta 0. So the sum of squares residuals is as small as possible. Okay, so we have, you know, RSS is equal to the sum of basically y minus y hat squared, and you know, this is beta 0 plus beta 1x, and we want to pick the beta 0 and the beta 1 so that this thing is as small as possible, right? Pick beta 0 and beta 1, so RSS is as small as possible. Okay. In 100B, did you guys talk about how OLS is the blue, the BLUE, the best least unbiased estimator. Okay, right. So so what does that mean? What does it mean for the estimates to be the blue? It's unbiased, right? Okay. So we'll say well, there's a condition there, right? It's if the predictors are uncorrelated. Okay, so there's a condition there, right? So if the predictors are uncorrelated, OLS will provide the blue, right? So OLS finds best linear. I'm like, what am I doing? Best linear unbiased estimators. Okay. Okay, and so unbiased means what? This means that if somebody else gets a different data set and somebody else gets a different data set, and we keep using this, then in the long run, the average of all of our estimates will be equal to the true values of these parameters, right? So in the long run, different values of the estimates from different data sets I'll say based on different data sets, will average to the true parameter values. Okay, so OLS will lead to in the long run, will average out to the true parameter values always, okay? And then what does it mean for the best part? The lowest amount of variance, right? So the lowest amount of variance in the estimators. Okay, meaning that, again, okay, so maybe this is the true model, true relationship, and then, you know, one data set looks like this. And so the maybe the this is like one fit for a data set. Okay, and then maybe another data set has like these points, right? Based around the true model, and maybe it looks like this, and this is like you know, another possible fit. Okay, and what this says is that the kind of the variation that we see between one fit and another, we're going to have the least amount of variation if we're going for unbiased estimates. So unbiased means that in the long run, if I take different fits based on different random data sets around the true model, right? So if I average the green line and the pink line or the red line or whatever it is, and I do this a whole bunch of times, in the long run, all of those averages will be the true relationship. That's the unbiased part. And then the best part is that the values like will vary as little as possible. That's the best part. okay? And so OLS tells us that this is what we're going to get, okay? And so we might say, well, that's pretty good. Why would we ever want to do something different? Why would we ever want something other than OLS? Because OLS, we like OLS. OLS is generally a good thing. So why would we want to do something different from OLS, okay? And our book says there's two things. One is prediction accuracy, okay? And then the other part is model interpretability, okay? Which kind of fits in with the overall themes of what statistical learning is all about, right? Statistical learning is all about trying to make good predictions and trying to get inference or understand what the relationships are, okay? So, so prediction accuracy, so let me just write this down. Why do something other than OLS? Okay, and so yes, one is prediction accuracy, and I feel like I just want to copy this entire paragraph here. But basically, so OLS works best if you've got a lot of observations and not that many predictors. If the number of observations is way bigger than the number of predictors that you have, right? So if you have like 3 predictors and 500 observations, great. OLS is going to do well, right? Okay. But you might be in a situation where you have lots of predictors, right? You might have where N, you still have more observations than P. Maybe you have 100 observations, but now you have like 70 predictors, okay? Because whatever it is, you've got like, you're collecting variables on everything. You're not quite sure which variables you want to use, so you've got like 70 variables, and then you only have 100 observations or something like that, okay? All right, I mean, and then so in that case, okay, if the number of observations is not much greater, okay, so if N is only a little bigger than the number of predictors P, then what kind of problems do we run into? Yeah, we get overfitting, and basically the coefficient estimates are highly, highly, highly variable, okay? Then, yeah, the coefficient estimates are highly variable, and that can lead to overfitting. And so just basically what data you have in your data set right now will be will really influence what your coefficient estimates are. And if somebody else takes another random set, they might get entirely different coefficient estimates, right? So if you have a situation where you only have like 3 predictors and 500 observations, and I do OLS, and then you take another random data set with 500 observations, 3 predictors, and you do OLS, your coefficients will be a little bit different from mine, but they should be in agreement, okay? But if we've got a bunch of predictors, and you take a random data set, and I take a random data set, and you do OLS, and I do OLS, we're probably going to experience a lot more variability, okay? Okay, and then I don't know how often this happens, but if this happens, where you've got more predictors than the number of observations, then OLS fails, right? OLS, like you're gonna get, what does R say? You get this error when you basically have more predictors than observations. Is it like the matrix is invertible? Something. I think it says like trace, you have a trace of 0. Let me see. Okay, let me just try x1 is going to be 1, 2, 3. X2 is going to be 1, 2, 3 plus R norm 3, and then X3 is 1, 2, 3 plus R norm 3, and X4 is 1 to 3 plus R norm 3, and then Y will be 1 to 3 plus R norm 3. Okay, so now we just got a bunch of noise, right? And if I try to do LM is Y as explained by x1 plus x2 plus x3 plus x4, oh, I guess it still did it. Okay. I guess it just uses the first two and then throws away the other ones or something. But if you tried to do, okay, I guess I didn't know what R was going to do when you did something like this. But yeah, okay. I guess it just ignores predictors 3 and 4. Okay. But I guess, you know, somebody else, if they had put the variables in a different order, right? Like if I did x3 and x2, right, we would get something different. Okay, so yeah, I guess it depends on the order in which you put the variables and stuff, which shouldn't matter, but anyway, you can't, basically you can't do this, right? If you've got more predictors than observations, then it fails. Okay, and so one thing we can do, a solution is to constrain or shrink the estimated coefficients, okay, are highly variable. All right, so one solution is constrain or shrink the coefficients. Okay. And then the other part, for why do something other than OLS, is model interpretability. Okay. And basically for model interpretability, basically models that have fewer variables, fewer predictors, are easier to understand than models with more predictors, right? Okay, and so can we perform some kind of feature selection, right? So the solution here is some kind of feature or variable selection. Which predictors in X do we use? Okay, we don't want to use all of them. If we've got a lot, maybe we only want to use a few. And so, so that's why we might do something other than OLS, okay? Because OLS just says, take all your things, dump them in there, and get coefficients. Okay, so these are kind of the solutions that we've got: subset selection and shrinkage, which I've mentioned already, and then another one is dimension reduction. Okay, so another solution that addresses both. Is dimension reduction. Okay, all right, so subset selection. All right, so this is this should have been covered extensively, I think, in 101A, okay, for linear regression. And but I guess I'll just kind of blitz through this. Okay, so best subset selection. This is like, I guess, the ideal scenario in that you test out every single possible combination of variables, okay? So if you have p variables, p predictors, there's going to be 2 to the p predictors, because it's basically, do I include variable 1? Yes or no. Do I include variable 2? Yes or no. Do I include variable 3? Yes or no. Do I include variable 4? Yes or no. And every possible combination. So you'll have like 1, 2, 3, 4 are all included. And then you'll have 1, 2, 3 is included, and then 1, 2, 4 is included, and then 1, 3, 4, and then 2, 3, 4. And then you do like choose 2, and what is that? 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. And then, you know, there's a lot of these things, right? So you've got, you're going to have 2 to the p possible models, okay? So best subset selection is basically check all possible combinations of variables. Okay, and then choose the best one. All right, and then best I put in quotes because how we define best may not be entirely clear, okay? So best subset selection is basically check all possible combinations of variables, and then maybe I should say, and then do OLS for each of these things. So and then fit an OLS model, least squares model, for each combination of variables, each subset of variables. Okay, and then choose the best one. And then the best, how we define best, you can use AIC, BIC, adjusted R squared, or kind of validation / cross-validation error. Okay. The unadjusted R squared is not there. Why? Why?
Because it'll go up with the more predictive
budget. If you use the regular R squared, unadjusted, it's always going to go up if you add more predictors. So it's going to just say, use all the variables. This gives us the best result. Okay, so that's we don't want that, right? So unadjusted R squared will always choose all predictors. Okay, and so for AIC and BIC, and so this is basically AIC lower is better, and BIC lower is better, and adjusted R squared higher is better. Okay, and then validation or cross-validation error, lower is better. Okay, do you guys remember what AIC, BIC, and adjusted R squared is? Other than like what the letters stand for, right? Akaike, information criterion, and Bayesian information criterion, and adjusted R squared. You remember the graph? they go down, right? More predictors, they go down generally, and then they starts coming back up a little bit. Well, the difference between AIC and BIC, huh? Yeah, okay, so let me, where is this? This is somewhere in here. Okay. Oh, yeah, and then they have CP, which is the same as AIC, basically. Okay. So yeah, so these are the graphs. This one is CP, or which is pretty much the same as AIC, okay? And this one's BIC, and then this one's adjusted R squared. And so this is, it goes down as we add more predictors, and then it starts to come back up. Same with BIC, it goes down as we added more predictors, and then it starts to come back up. And then adjusted R squared, it goes up as we add more predictors, and then it starts to come down if we add too many predictors, right? And basically, both of these introduce a penalty for having too many predictors, okay? And BIC basically imposes a heavier penalty than AIC. So what that means practically is that BIC will favor fewer predictors than AIC. So BIC, it says 4 is the best number of predictors, and AIC or CP says 6 is the best number of predictors. But if we look at this, you know, the difference between 4, 5, and 6 on this graph is like nothing, okay? I mean, I guess there's a difference, and we ask what's the minimum. It's 6 is the minimum. And over here, the difference between 4, 5, and 6, again, is quite small, okay? Similar for adjusted R squared. 4, 5, 6, actually adjusted R squared, I think, says 7 is the best. And, but they're all, like, the amount of difference that you get is different. And basically, okay, so this is AIC, which is basically you take the total sum of squares, and then you add in a penalty for more predictors, right? And here the penalty is basically 2, and here the penalty is log n. Okay, so as long as log of n is bigger than 2, which is almost always, this is a bigger penalty for the number of predictors. D is the number of predictors. So you're for each additional predictor AIC, this thing goes up. Okay, so and BIC, for each additional predictor, this thing goes up as well. Okay, and so so basically log n is a bigger number than 2. So so this basically imposes a heavier penalty for more predictors. Okay. Lower is better. I don't know, where do I write this? Okay. So this is basically RSS plus 2 times the number of predictors, sigma squared, and this is RSS plus log n times the number of predictors times the variance, okay? And then there's just some proportionality thing, right? Something proportional to it, okay? And basically, BIC places a heavier penalty on additional predictors. Than AIC. So it will favor models with fewer predictors. But I don't know, like, if somebody said, well, which one should I use? Should I use AIC or BIC? Or adjusted R squared? My answer is like, I don't know. It's hard to say, this number is the best number in all situations at all times, okay? And in a situation like this, if this is what your BIC it stopped responding. Oh no. Okay. That works. Okay. Oh, now we're working again. Okay. If this is what your graphs look like, and you say, well, should I include the 5th predictor or 6th predictor? My answer is, I don't know. Like, what do you think? I guess you want to ask, like, hopefully you have some context of these variables, and you can say, like, well, does it make sense to actually include these additional things? Maybe I want the simpler model where I only have 4 predictors. That's easier to understand, right? Or maybe for me it's most important that I squeak out just a few little extra sliver of better predictions, right? And so maybe I do want to include a couple more predictors, okay? So you have that AIC, BIC, and adjusted R squared. Adjusted R squared does basically is like RSS, but is like R squared, but it introduces you're dividing it by every additional parameter, like, reduces the RSS a little bit, right? So that's adjusted R squared. And then lastly, you have the validation and cross-validation error. And this is probably where things have been shifting towards, okay? As far as machine learning goes and stuff like that, things have been shifting towards away from AIC, BIC, and adjusted R squared, and moving towards, let's just use cross-validation error. And the model that's going to give me the lowest cross-validation error, that's the one I'm going to use. That's a lot of things have been kind of shifting towards that, because it avoids the situation where we have to say, well, which judging criterion should I use, right? Should I use AIC or BIC or adjusted R squared? And there's something inside of you that says, well, I'm not quite sure. And so we're I don't know if this is good or bad, but we're kind of giving up our responsibilities, and we're avoiding making decisions, and we're just gonna let the computer and the cross-validation, I mean, that is in of itself a decision, right? Like, I'm gonna do cross-validation error, but I guess there's a little bit less that you have to defend, right? Like, if somebody came and said, you picked this model because you chose the AIC criteria, and I want to know why you chose AIC versus BIC, and then you're on the spot and you're like, well, I thought it was a good number, but you don't have a good justification. Whereas cross-validation, I think it's a little bit easier to justify, right? You just say, well, I wanted to kind of get an estimate of how well it's going to do on, for test observation error. I think that's easier to justify. So I think so things have generally been shifting towards using cross-validation error. And if you if you use sklearn in Python, which we're not going to do in our class, pretty much everything is centered around cross-validation. All of your decisions about which model to pick is centered around cross-validation. I don't think sklearn makes it easy to get AIC. or I don't know, maybe, let's see. I've never tried. In Python, you have stats models that will give you AIC and BIC, but I've never actually tried to get AIC or BIC out of sklearn, and I don't even know if it's possible. So cross-validation error, this is kind of things are moving towards using this. Can you do AIC in sklearn? Is it there? You don't. Yeah, I don't know if it's possible. I've never tried. Let's see. Oh, they do have it. Wait. So you got sklearn, linear model. Let me see. AIC. Huh? Lasso model selection, cross-validation, AIC, BIC. Okay, so, all right. Yeah, I guess they do have it for the lasso. Okay, so anyway, so that's what we have there. Let me see if there was anything else I need to say. Okay, yeah, so this is for the validation, cross-validation. So this is, if we use the BIC for the number of predictors, it says 4. And then when we go for, this is one random validation set, which we know has issues of being high variation. And then this is tenfold cross-validation. You know, they both kind of selected 6 predictors. But again, for our simulated data, do we use 4, 5, or 6 predictors? Probably doesn't make a ton of difference here. Okay, but I don't need to re-explain how we would use the cross-validation error on this, do I? Or we're okay? Okay, so that's, you know, best subset selection requires us to test out every single possible model, which we probably would rather avoid. Okay, I guess, you know, depending on your computational power, doing every single model might be possible. Okay, the other ones are forward stepwise and backward stepwise selection, and I think again this was covered extensively in 101A. So with forward stepwise selection, you start off with no predictors, and then you try out one predictor at a time, and then you say, okay, I added it. I have all the models where I use one predictor, and which one's the best, right? Which one has the highest RSS? And you say, okay, we're going to pick that one. And then now you have that one, and then you try adding one more variable, okay? And then so you say, you know, so maybe the first time, variable 3 was the best variable to use, okay? So variable 3 is locked in, and now you try out every other variable. You try variable 1, variable 2, variable 4, variable 5, all of those other variables in addition to variable 3. And then you say, okay, which one was the best there? And you lock that one in. And you do this until you end up selecting every single variable, okay? And then so you slowly go from no variables to one variable to using 2 to 3 all the way up to the end. And then you go back and you use AIC, BIC, or adjusted R-squared or cross-validation error or something to pick the number of predictors, okay? And so that's forward stepwise. Backward stepwise selection is pretty much the same. You start with all of the variables, and then you say, okay, well, let's try the models where I've removed one, and you try removing each one at a time, and you say, okay, the one that affected me the least was when I removed this variable. So we'll drop that one. And then you try dropping one more variable, and you work backwards, one variable at a time until you get down to 0, and then again you use AIC, BIC, or cross-validation error or something to pick the thing, right? So so forward, stepwise. Okay, so you start with 0 variables. Okay, add. Okay, so so then we'll say test all models with 1 variable. Okay, and then you choose the best model. So this is highest RSS, highest regular old RSS. Choose the best model that uses only 1 variable. Okay, and then test all models where you use the previous variable plus 1 other variable. Okay, previous variable, so this one is quote, this one is locked in. Okay, 1 more variable, so this is test all variables 1 at a time. Okay, and then repeat until you have a model with all variables. Okay, and then and choose the number of predictors using AIC, BIC, or cross-validation, adjusted R-squared or cross-validation, right? Okay, and then backward stepwise is the same thing but backwards. Start with all variables, remove 1 at a time, until 0 variables. Okay, and then choose the number of predictors. Okay. Are there any questions on this? We're good. Okay, and then and I think R has an automated thing to do this, right? You just say step select something. What? Yeah, it's somewhere. It's somewhere. It does it automatically, right? It just kind of lists every single possible model, and then where is it? Regression subsets. Yeah, and then it goes through and it picks them. Okay, it picks the models for you. All right. And again, I think this should have been covered in 101A, but it's okay to see it again. Did I mess up? Oh yeah, sorry. Highest R-squared or smallest RSS. You are right, you are right. Highest R-squared or lowest RSS, right, exactly. Okay, good catch. Uh, yeah, we don't want the highest RSS, which is infinity. Okay, so that's subset selection, and it works. You know, forward stepwise selection, it's not guaranteed to give you the best, but in general, you get pretty good results, okay? Like if you checked out every single possible model and then you did forward stepwise selection, I think they had like a comparison somewhere. Which one does it better? Okay, so when you did, you know, for forward stepwise selection, they started, you know, rating was most important, okay? And so this one is locked in, and then with two variables, then with rating locked in, they tried every variable, and then income was the next most important. And so that gets locked in, and then with three variables, student was the best, and then with four variables, with rating, income, and student all locked in, then with four variables, rating, income, student, and limit is what you would select with forward stepwise selection, okay? But then with best subset, or checking all possible combinations, with 1, 2, and 3, rating, income, and student are in the same. But actually, when you go for 4 variables, I don't know how this happens, but it does. It's actually rating doesn't really contain more information than what income, student, and limit and cards contains. And so actually, if you're going to go for the 4 best combination of variables, it's going to be cards, income, student, and limit, which is crazy that rating no longer matters, but that's what happens, okay? And you would miss this. You would miss this kind of information because with forward stepwise selection, once you've selected something, it's locked in, okay? And it's true that it's possible that in the future, if you have more variables, like something that you thought was important earlier is no longer important, right? So yeah, so what you thought was important in the past may not be as important as you had always believed in the future. Which life lessons from forward stepwise selection. Okay. Yes? Yes, there is mixed selection where you go forward and you go backwards. I guess, I don't know. Let me think. How does going? Okay, so let's see. The hybrid approach, forward stepwise and backward stepwise, generally but not identical. Another alternative in which variables are added to the model sequentially. However, after adding each new variable, the model may also remove any variables that no longer provide an improvement. Such an attempts to more closely mimic best stepwise subset selection. So I'm trying to think. So I think basically you add one variable and then you add a second variable and then you try removing the first variable that was normally locked in, and then you try adding like you lock in the second variable and then you try like adding one of the other variables, and then you say, okay, well, out of there, which's the best two thing, and then once you got like those two locked in, then you add a third, and then you can try removing some, I don't know. It seems like just a more complicated way of doing checking all 2 to the p models. So this doesn't give a specific approach. Okay. All right. Okay, so that's subset selection. All right, and our next section, let's see. I guess we could do a break now. You don't want a break now? Okay, we'll do a break. All right. Okay, so we're moving on, and this part is on shrinkage methods, okay? And if you've taken 102B with me, we've seen these things before. but they are worth repeating because you know, we'll focus less on the kind of the algorithmic side, but just kind of like the implications of what doing something like ridge regression or lasso has on kind of the coefficients and the estimates here. Okay. All right. So so we'll call these shrinkage methods. And this is ridge regression and lasso. Okay, so earlier what we had was when we did subset selection, we used least squares estimates. We said here are I'm going to use this subset of variables, and with this subset of variables, I'm going to use least squares criterion to pick the parameters, and then and I'm going to compare using this subset versus this subset using something like AIC or BIC or cross-validation error. Okay, but the parameters were estimated using least squares, the least squares method. We said I want to minimize the RSS. I want to pick beta 0 and beta 1 and beta 2 and beta 3 or whatever those are by picking them so it minimizes RSS. Okay. Now what ridge regression does is it says, you know what, do not minimize RSS only anymore. Okay. When you pick your coefficients, the thing that you should minimize isn't RSS, but it should be this thing. Okay. So don't minimize just the RSS, but minimize this thing over here, okay? So, so the other methods, we pick beta by choosing the betas to minimize RSS. With shrinkage methods is we pick our betas, okay? Beta values by minimizing a different, minimizing a function that is slightly different from RSS. Okay, so you know RSS is the sum of this, okay? And then so for ridge regression, it says pick betas to minimize RSS plus lambda times the sum of the beta squares, okay? From j equals 1 to p of beta sub j. All right. So this is basically minimize RSS plus, and we might call this a complexity penalty, or I don't know, just some kind of penalty over here. So we'll call this the penalty, and then this is kind of over here is the penalty weight. Oops. Something happened. Okay. And so so now when we pick the betas, okay, if we pick a large beta, this thing goes up, okay? So if the coefficient, so what this effect has is if the coefficient beta is big, then this term, lambda beta j squared, will get bigger as well. Okay, and so now we have kind of these competing things. One is, well, we want to pick the betas to minimize the RSS because that's part of this equation. Okay, so we still want, we don't want RSS to get huge, okay? But at the same time, if minimizing RSS requires beta to be large, that's also going to introduce problems here because that's going to cause this thing to be big, right? So it's kind of just like, you know, when you're making a decision about something, now you have kind of competing priorities, right? So an example that I use is, you know, maybe you're choosing a place to rent, right? And you say, well, how do I pick the place to rent? And if to you, the most important thing is lowest cost of rent, right? To have the lowest rent because you're on a tight budget, then that might be akin to just minimizing RSS, right? So you might say, I need to just, if the strategy is just pick the place that minimizes the rent, you're going to just pick kind of the cheapest apartment to live in, okay? But what could end up happening is that the cheapest apartment to live in might be an hour away from work, okay? And maybe that's not an ideal situation. And you want to live closer to work so you don't have to commute as far, but to get closer to work, you have to pay more rent, right? And so now you might say, well, I need to pick the apartment by kind of the one that's going to minimize the rent, but also there's a competing thing which says I want to minimize my drive time to work, okay? But you need to have something that weighs, you know, each additional 10 minutes of drive time is going to be worth this much in rent money to me, okay? And you can say, well, I'm willing to pay an extra $50 a month in rent if that means I'm going to save 10 minutes on my drive or something, you know? Or, you know, I'll pay an extra $100 a month if it'll save 20 minutes on my drive, right? And there's going to be something, and you'll have to try to find the sweet spot of maybe I'll pay more for rent. I'm willing to raise RSS, okay? I'm willing to pay more for my rent if it means keeping this part, like my drive time, down, okay? Except it's not drive time and rent, it's RSS and this beta penalty. Yeah, question?
So the betas are standardized?
Not necessarily. A lot of times we will standardize. We will standardize our X's, but we don't always. And so depending on the situation, you might, so depending on the situation, you might want to standardize your X's and you might not want to, right? So if the X's are measured in different units, then it makes sense to standardize them, right? But you might have X's, like one column might be cost of, I don't know, like it might be like different cost variables, right? And they're all measured in dollars, okay? And so in that case, you probably don't want to standardize them because then it will, because one thing, like one of the variables will be like cost of the, I don't know, the sticker or something, right? And so maybe they only vary like from, you know, 20 cents to 25 cents. And so to standardize that suddenly makes the difference between 20 cents and 25 cents like a huge difference versus like the cost of, I don't know, the engine where it's like, I don't know, thousands of dollars versus, you know, $10,000 or something like that. And so, so maybe it makes sense to say, well, the cost of the sticker is not important, so we're not going to It's the actual cost that matters, right? So so maybe we standardize, maybe we don't. It depends on the context, right? So if it's something like probably dollars, you probably won't standardize if they're all in the same units, because then suddenly, because standardizing basically emphasizes the variance that exists within the variable, right? So if the lowest cost is 20 cents and the highest cost is 25 cents, then 20 cents will become like a -2 and 25 will become a +2. And if we're talking about the engine where the lowest cost is 1,000, the highest cost is 10,000, the 1,000 becomes a -2 and the 10,000 becomes +2. But probably if you're making some kind of prediction thing, depending on the context, again, maybe it is more important that 10,000 is represented as 10,000, and like what happens with the 20 cents and the 25 cents doesn't really matter. So, but yeah, if we're talking about different units, like someone's cholesterol levels versus like their blood pressure or something, then it might make sense to standardize those things. But yeah, the answer is always it depends, maybe on the context. So, but yeah, here, so in general, we want smallest RSS because RSS is a measure of how much error there is between our prediction and what the actual value is. But now we're balancing them out by saying, I don't want any of my coefficients to be too big. Okay, I don't want my coefficients to be too big. Okay, and this is called the shrinkage method because what ends up happening is that when you use ridge regression, all of the parameters beta are shrunk towards 0. Okay, ridge regression is going to favor betas that are a little bit smaller than what you would get if you used just regular least squares, where you're trying to minimize the RSS. If you're only trying to minimize the RSS, we're going to say, yeah, let beta be as big as you want. But now with ridge regression, we're saying, I want to minimize RSS, but at the same time, I really don't want a big beta value. Okay, so what benefit does something like this do? Okay, and so here's a picture of what happens. So this picture, just kind of on the left, basically says if your lambda, the lambda is how much penalty to apply for having a big beta, right? So when lambda is small, we're saying, okay, big beta, I don't really care. It's not a big deal to me, right? And then as lambda gets bigger, it says big betas are a bad thing. We don't want them, okay? And so what we can see is that if there's very little penalty, we're going to get values that are actually very close to the OLS things, okay? And so these are so these are the standardized coefficients, okay? So we end up getting something like -300 versus 400 and something income limit rating. And what we see is that as I increase my lambdas, it pulls these things, okay? Like limit gets shrunk down to 0, okay? And the coefficient on income started off as -300 and that gets shrunk down to 0, okay? There's an interesting thing that happens with rating, okay? Its coefficient used to be small, but as we increase the lambda, it actually kind of grows the thing to a certain point, and then it brings it down, okay? And then with student, this is either a kind of a 1-0 thing. And so we, again, when lambda is really big, and this is a log scale down here, when lambda is really big, it shrinks all the values down towards 0. But we get an interesting thing right here where the coefficient, okay, so again, this is something like the slope actually grows for the rating. In general, it shrinks everything down. But ridge regression also has this other side effect where it prefers that it doesn't want one variable to be huge and another variable to be small, okay? Because it's using the squared thing, it kind of prefers things that are more like, quote, a circle. And so rather than having one thing that's huge and one thing that's small, it would rather have two things that are kind of close to each other, right? So it's kind of like if you're thinking, like, if the penalty is take the number and you square it, okay? And let's say you have like 10 points to give. The extreme is having 0 on one and 10 on the other, okay? Then the penalty is 0 squared plus 10 squared, which is 100, okay? Whereas if you split them and you put 5 on one and 5 on the other, then the penalty there is 5 squared plus 5 squared, which is 25 plus 25 and 50, okay? So it prefers having your coefficients actually kind of closer to each other. But again, the big idea with ridge regression is that we're no longer minimizing just the RSS, but we're also tacking on this penalty for having big betas, okay? We call this the shrinkage penalty, okay? And the lambda is the tuning parameter which says how much penalty should we apply, okay? And so so when lambda is 0, the penalty term has no effect, and ridge regression is exactly the same as least squares regression, okay? And then as lambda goes to infinity, the penalty grows and the ridge regression coefficients approach 0, okay? Okay, so what benefit does something like this do for us, okay? It helps us in kind of the bias variance thing, okay? In that, so again, one of the issues with least squares regression was that you have variance in your estimates, right? Depending on the random set of data you have, the estimates of your coefficients beta can vary quite a bit, okay? And so what ridge regression does is it says, you know what? I hate it when betas get huge, okay? Ridge regression says, I hate it when betas get big. And so if least squares regression causes my betas to get big or small depending on the random data, ridge regression says, I hate that. I don't like that. So I want to make sure the betas stay small. And so it reduces the variance that we might see in least squares regression. It says, yeah, basically do least squares regression, but I really, really, really hate it when betas get big. So do something like least squares regression, but really make sure your betas never get big, okay? And so, and because of that, the betas don't vary as much, and so it reduces the variation that we see, okay? The side effect, though, is the bias goes up, okay? So we've reduced the variance in our estimates, but now if we do this in the long run and we take the average of all of our beta coefficients, we no longer get the true coefficients. They no longer average out to what the true parameters are. So we've introduced some bias, okay? So we've handled one issue. We said, okay, one of the problems with least squares regression is that we have high variation and sometimes the betas will get big. So ridge regression says, I really hate it when the betas get big. So we've reduced a lot of the variance there, but on the other hand, we've introduced bias, okay? And so that's what this kind of picture tries to draw. The bias is this black line. So as your penalty weight goes up, the bias goes up, okay? And then the variance, though, the variance goes down, okay? So with no error, this is basically least squares regression, and we have low variance. And what we see is that as we use a bigger penalty for ridge regression, the variance does indeed go down. Eventually, it goes down to 0. This is basically where your coefficients are all 0. Okay, and then and this is the the error for the test data set, okay? And so what we see is that, you know what, here at this point, this is kind of the sweet spot where we've reduced the variance quite a bit. We have, yes, we have introduced some bias, okay? But overall, our prediction error is the lowest here, okay? But again, if you've introduced too much bias, then the prediction error starts going back up, okay? So this is one way to kind of improve our prediction accuracy, is by reducing the variance in our coefficient estimates by saying, I really want to avoid a large coefficient, okay? So I'm going to go ahead and do this, and this is, I think this is the same thing, but I'm going to just kind of introduce this here. Copy this, we'll put this over here. Okay, so ridge regression reduces variance in our beta estimates. Okay, OLS has no problem with calculating a very large beta. Okay, ridge regression does not like large beta. Okay, so ridge regression basically says, do something like OLS, but just really make sure you don't get big betas, okay? Okay, so this effectively reduces the variance in our beta estimates, okay, at the cost of introducing bias. Okay, so this is bias. Okay, bias goes up. Penalty goes up. The variance goes down. And this is the test error rate, okay? And this is kind of minimum achieved with reduced variance and a little bit of bias. Okay, is that all right? Ridge regression? All right. So ordinary least squares regression is great, but ridge regression can outperform it in some cases by reducing the variation. Okay. The lasso. Okay, lasso looks almost exactly the same. All right, except what's different? The penalty is not beta squared, but it's the absolute values, okay? The penalty for lasso is that, having big betas is undesirable, okay? But with ridge regression, because you squared them, having a big beta was like not double, but like squared as bad, right? It was it was much worse, right? So going from 5 to 6, increases it from 25 to 36, so a change of 11 points. Okay, but going from 10 to 11 goes from 100 to 121, so an increase of 21 points. So that difference of adding 1 to a beta has a bigger effect when your beta is larger, right? Here, it's just the absolute value. So going from 5 to 6 increases it by 1. Going from 10 to 11 increases it by 1, okay? So, so lasso is almost the same as ridge regression, but we're not using, at least formulaically. So the lasso says pick betas, beta values to minimize basically RSS plus the sum of the absolute values of the betas, okay? So it looks very similar to ridge regression, but now we're using absolute values, okay? And surprisingly, this has a significant difference in the effect of what happens, okay? So ridge regression says, I really hate it when betas get really big, okay? Lasso just says, I hate everything, okay? I like it when beta is 0, okay? So ridge regression was like, I hate it when betas get big, okay? But small betas, we can have a whole bunch of small betas and I don't mind, okay? Lasso is basically big beta, small beta, I don't care. I only like betas when they're 0, okay? That's basically what lasso is saying. I really only like beta when it's 0, okay? That's when I don't induce a penalty. Anything that's a non-zero beta, you're gonna get a penalty. And I don't care if you're big or if you're small, everybody gets the penalty, okay? So that's what lasso does. And so what lasso ends up favoring is it's going to end up favoring models where beta ends up 0, okay? It's going to favor models where some of the coefficients for the variables get pushed down to 0. And because of that, lasso ends up performing variable selection for us, okay? So so that's what we get, okay? So lasso likes when beta is 0. Anything that is not 0 gets a penalty. Okay. On the other hand, ridge doesn't mind small betas. It only hates big betas. Okay, so ridge doesn't mind having a bunch of little betas, right? 0.1 squared is 0.01, who cares, okay? It just really hates big betas, right? So beta is 100, you're getting a penalty of 10,000, okay? That's bad, right? Lasso, everybody gets a penalty, and it's only satisfied when beta ends up 0, okay? So anything that's not 0 gets a penalty, so lasso performs variable selection. Okay, basically the terms that don't get a 0 beta are included in the model, and everything else is not included in the model, right? So lasso performs variable selection. Okay, it yields sparse models or involves only a subset of the variables, okay? And so we can see this is what ends up happening is that as the lambdas go up, the betas get, the coefficients get pushed down to exactly 0, okay? And if we kind of, only if we relax these, then the coefficients are allowed to kind of grow. Okay, here is, these are like another way of doing this, okay? You can think of ridge regression and lasso as kind of these constrained optimization problems, okay? Where we minimize the RSS, but we constrain it to some kind of constraint. And so here is lasso says constrain it so that the absolute values are less than some set number s, and here's where the beta squareds are less than some set number s. And so what that picture ends up looking like, where is it? Okay, is the lasso, you end up getting a constrained thing where let's sneeze, maybe not. Where the constraint ends up looking like a diamond, okay, because of the way absolute values work. Is that anything along this line ends up looking like a diamond. And so what ends up happening is that it ends up preferring like finding the optimal solutions at corners, okay? And what a corner means, okay, it means that one of the variables is 0 and the other variable is not 0, okay? And if you extend this into hyperspace, okay, you'll still get corners of these, or what are vertices of some polyhedron, okay? And that's where basically one or more of the variables are 0 and the other variables are not, okay? Whereas with ridge regression, because it's a squared thing, okay, where all the variables are squared, you end up getting a circle or a sphere, and so you end up getting values that are not at the corners, but something around here, okay? So that's just kind of what the constraint functions look like. It's not, I don't know. Don't worry too much mathematically about this, okay? But this picture shows up like on Wikipedia and stuff, and if you're just kind of wondering like, what does this picture even mean? It's the idea of, you know, you're minimizing the RSS, okay, which is going to be this quadratic or ellipsoid type thing, okay, and yeah, you're trying to find the minimum, like where's the closest you can get towards the. This is the OLS solution, and we want something as close to the OLS solution as possible, but we impose some constraints. We say, I don't want betas to be really big, or I really like it when betas are 0, and this is what we end up getting. Okay, is that okay? This is similar for, and so similarly, lasso reduces variance, okay, because it prefers where the betas are 0, okay, and so if betas are 0, then you have no variance on those betas. And so lasso also reduces variance. Again, it also introduces bias. And so, you know, your prediction performance can actually improve, right? You might get lower test error by reducing the variance in your estimates, even if it comes at the cost of introducing some bias. Okay? So you can get better prediction and performance. With lasso, because it does variable selection, you might have greater model interpretability because now you have a model that uses only a few variables, so it's easier to deal with. Okay, and so here's, you know, do your reading, and it talks a little bit more about lasso and ridge regression. Okay, selecting the tuning parameter. This is always kind of tricky, like what value of lambda should we use? And generally we say, let's do cross-validation, okay? Let's just try it out. Try out different values of lambda, and we'll just see what our performance is on our cross-validation error, and we'll pick the lambda that produces the smallest cross-validation error. Okay, and almost all of these curves, there's like a sharp at a certain point where it really takes off. We see it. We see it here, right? It goes down. Like where it goes down is gradual, and then suddenly it just rockets up. Okay. Similar here, it goes down gradually, and then it kind of rockets up. This is kind of a common thing that we experience when we're picking our tuning parameters, because so it goes down and it kind of shoots up. What's basically happening is as you increase that lambda, you're increasing the amount of penalty, and so in the beginning, the amount of penalties, the penalties are small, and it doesn't really have much of a difference. It's kind of like how often does somebody break like park illegally, right? So the penalty for getting a parking ticket is probably like 60 or 70 bucks, right? And if they increase that penalty from $70 to $75, is that really going to change the how often somebody parks illegally? Probably not, right? Like you'd say, I don't want to get a parking ticket, but the difference between a $70 fine and a $75 fine is probably not going to really make a huge impact, right? But all of these things are on a log scale here, and so if we move from like over here to over here or something, it might be like parking illegally the penalty is no longer $75 but $7,500, right? And if the penalty for parking illegally is $17,500, you're just gonna be like, I don't even want to drive anymore. I'm gonna avoid parking. Like I really don't want to take risks of parking, right? Because the penalty is just so steep, right? And so what ends up happening is you end up introducing a bunch of issues by having too much of a penalty on the system, where basically you're saying, I really like it when beta is 0, and so the model ends up picking 0, all of your coefficients to be 0, and so you're going to have tons of cross-validation error. It's a terrible model because all of your coefficients are now 0. Okay. Oh, we're going to run out of time. Okay, the last thing is dimension reduction. All right, and this is a little bit like jumping ahead, but it's brought here. Okay, we do something called principal components regression. Okay, and there's all of the symbols and stuff. Okay, what principal components does is it tries to find a way to reduce the number of dimensions in your data, okay? And it does this by finding the axis upon which the variation is the greatest. And it says this is the most important, quote, direction in the data, okay? So here, here's a graph of population and ad spending, and it kind of has all of this variation and stuff. But it says, you know what? The most important thing, okay, these two things are highly correlated, and there's something that's kind of this, maybe I don't know, market importance score or something, and we can just reduce all of our data into basically one of these directions here, okay? And that's basically, so if you think about your SAT score, okay? I don't know if you had to take an SAT score or something, right? You take like different tests. There's like the verbal and then the math, right? And so there's technically 2 dimensions, okay? But you can also, rather than saying like, oh, I got 800 math and 600 verbal or something, and somebody else says, I got 800 verbal and 600 math, okay? You can also just report your total score and say, I got 1400 on my SAT or something like that, okay? And yes, you lose information because the person who got 800 math, 600 verbal, and 800 verbal, 600 math, they both have a score of 1400, okay? But overall, we would say, 1400 on the SAT, that's pretty good. We're gonna, you'll kind of put them in a similar category, right? And so at a school like UCLA, they probably just look at the composite score rather than the individual scores. That's something, right? But maybe at a school or maybe the engineering school is different, where they say, okay, you know what, the math part is more important, and so we really want to make sure students have over 700 on their math SAT or something, and then the verbal score, we just want to make sure they're above average or something, over 450 or over 500 on the verbal part or something. So you might want to have both variables, okay? Or you might just say, well, let's add these two together, okay? And in fact, so what the engineering school that might say, like, the math is more important than the verbal, they might say, you know what, we have our own system, and we're gonna take your math score and multiply it by 2, and we're gonna take your verbal score and add it only once, right? And so in that case, we're kind of weighting the math part twice as heavy as the verbal part. So 800, 600 on for math verbal would end up being what? 800 times 2 is 16 plus 6, so 2200 versus 600, 800, which is, I don't know, what is that? 2000, right? And so that makes a difference. Okay, and that's basically what principal component analysis does, is it says, you know what, let's take our variables and just weight them different amounts, and that's what this thing represents. It says, like, just weight this variable by this much and weight the other variable by that much. And it just says, let's weight them differently, and the way we weight them is, we use these eigenvectors and stuff, but it doesn't matter. Just we're going to say we're going to combine the variables in a certain weighting, and by that we can reduce the amount of variables that we have to deal with. Okay, and so principal components regression basically says do PCA on the data first, and when you do PCA, you've reduced the number of variables down to a smaller number of variables. Okay, so no longer you have population and ad spending, you now have the first principal component and the second principal component, which actually, if you look at this, contains the same exact information. It's just a rotation of the data. And then you do linear regression on just one of the principal components. Okay. And if you do it right, then a lot of times, so here is, we're trying to find a relationship between population and ad spending. Here you can just do regression on just one of the principal components. Okay, you can do population versus the first principal component, or ad spending on the first principal component, and you end up getting kind of these similar graphs. And basically, it turns out that only the first principal component matters, because if you do regression on the second principal component, it's not zero correlation, but very low correlation, okay? And so, so you can end up getting dimension reduction, okay? So, let me just think of maybe it's easier. I don't know if this is easier. So if you look at a data set on house prices, there might be a ton of variables. Variables like square footage of the house, how many bedrooms, how many bathrooms, square footage of the basement, square footage of the lot, all sorts of stuff. And then there might be like kitchen quality and bathroom quality and carpet quality and like just things of like how the amenities and how nice the house is. And then there might also be variables about the neighborhood, like the median price of the neighborhood, the crime rates of the neighborhood, the school ratings and stuff like that, okay? And so you might end up having like 30 or 40 variables in your data set. And you can do a regression on all 30 or 40 variables, and it might turn out that only a few of those variables are important, okay? What principal components regression will do is it says, you know what, before we do the regression, let's see if we can reduce the number of variables, okay? And if you do principal components analysis on a housing data set, you might end up getting 3 principal components, okay? And roughly translated, the first principal component might be related to how big the house is. The second principal component might be related to how nice the house is, right? Like, does it have wood floors and granite counters, or is it like, are the walls gross and disgusting, right? And then the third one might be like how nice the neighborhood is, okay? And so basically now you've reduced something complex about a house with 50 variables down to something a little bit simpler with 3 variables. Big house, big or small house, really nice and modern or old and falling apart versus nice neighborhood or junky neighborhood. And maybe just those 3 variables will be enough to fit a good regression model on the price of a house, okay? So principal components regression basically says, take the variables you have, do principal components analysis to reduce the number of variables you have, and then do linear regression, okay? And that's what basically all of this stuff says. And that's what we have. Okay, high dimensional data, let me see. Yeah, I guess you read the section on high dimensional data. It's basically a bunch of warnings of things that can go wrong in high dimensions, okay? In high dimensions, you can have all sorts of issues because of great variation there. Okay. The labs cover basically these different methods that we've covered today. And then and I'll assign a few problems from the homework as well for chapter 6. I'm finalizing kind of the details of the final project, and if you want, you can work alone or in partners, and I'll try to get all of the details by Wednesday for you guys. Okay. All right. We'll see you then. And yeah, have a good day.